Welcome back to the deep dive. Today we are strapping in for a really high-speed tour through the future of information itself.
We're talking about AI-generated content, or AIGC.
Exactly. And more specifically, the material that powers it all, synthetic data. This whole area moves so fast, and it has these profound implications for global security and, frankly, just our basic understanding of what's even real anymore.
It really does.
When we were looking at your sources, what just blew me away was the sheer scale of it, the speed of this digital takeover. The data shows the internet is just, rapidly saturating with artificial information, and telling what's authentic from what's not is becoming a Herculean task.
Right.
I mean, to put a fine point on it, just look at deepfake news. In 2018, researchers found exactly 0 deepfake news topics.
0.
And by 2024, that number exploded to 24. We are just flying into a world defined by this information saturation.
And that rising tide of artificial content, it's all powered by what we're talking about today, synthetic data. It is the engine of modern AI.
Okay, so define that for us. How is it different from just, a photo I take on my phone?
Well, unlike data we collect from the real world, like that photo or sensor input or document synthetic data, is created entirely inside the digital world, artificially.
But it's not just random noise.
Not at all. And that's the key. Its purpose is to be meticulously designed to reproduce the statistical characteristics and the properties of real-world knowledge. It's not just fake, it's statistically accurate fake.
So our mission today is to really get under the hood of this.
Exactly. To understand how this crucial data is made, why it's become an absolutely non-negotiable requirement for high-stakes fields like international security, and maybe most urgently, how we can build the tools to detect it, to verify its quality as this flood just keeps rising.
Okay, let's unpack that core problem. If we're being flooded by information and defense organizations have, massive satellites and sensors collecting real-world data all the time, why can't they just use that? Why is artificial data an imperative?
It really comes down to 3 things: scarcity, quality, and relevance. I mean, AI offers these incredible opportunities, especially for autonomous systems in defense.
Right.
But these systems need huge, diverse, and very specific data sets to train on. And real-world data, even when there's a lot of it, is often scarce in the exact way they need it.
So you see these consistent challenges across defense strategies everywhere, right? The UK, Australia, Canada.
All of them. And they fall into 2 big buckets. The first is organizational, it's data management. This isn't really a technical failure, it's a structural one.
You mean like data just sitting in different places, not talking to each other?
Precisely. You have data in silos, no common data standards, and this cultural issue where data needs just aren't considered early enough when they're building a new system. So analysts literally end up, and this is a quote, drowning in data that's either obsolete or unreliable by the time they can even use it.
So the problem isn't the volume of data, it's the utility. It's like having a library full of books written in 100 different languages you can't translate efficiently.
That's a perfect analogy, and that leads right into the second, deeper problem: data quality.
Okay.
Even if you can get to the data, real-world data can be incomplete, or it's labeled wrong, or it's fundamentally biased. Now, magnify that problem with the reality of operations.
You mean out in the field?
Right. Autonomous systems, especially uncrewed vehicles, they're dealing with just brutal conditions: dust, smoke, camouflage, vibrations. And on top of all that, you have deliberate adversarial actions: spoofing, data poisoning, signal jamming. Real-world data is inherently messy and, frankly, dangerous to collect.
So synthetic data becomes the necessary fill-in. It's the tool you need to improve the quality and utility of your training data sets, especially when it's just too impractical or way too dangerous to rely only on what you can see in the real world.
It's essential. Not a silver bullet, but essential.
Now that we get the why, let's look at the how. How is this artificial reality actually forged? I see 3 main paths, from, simple rules to really complex machine intelligence.
Yeah, the baseline method is what we call rules-based methods. This is where a human defines the data structure, like a CSV file or something, and then writes specific parameters and rules that the synthetic data has to follow.
And the upside is?
It's cheap, it's modular, and it's easy to understand what's going on.
But the drawback has to be huge.
Oh, it is. Scaling is a nightmare. If you need complex interactions, the number of rules just explodes. But here's where it gets really interesting for security. Because a human developer defines the rules, any bias they have, whether it's conscious, like business logic, or unconscious, like societal or gender bias, is directly and explicitly encoded into that data.
Whoa, so doesn't that make rules-based methods maybe the most dangerous for encoding bias? It's not some emergent thing, it's intentional, even if you didn't mean to apply it that way?
It absolutely does.
Yeah.
The bias is fundamentally deterministic. It's baked right in.
Okay, so what's the next step up in complexity?
That would be agent-based models. This is a proven simulation technique where you model different agents and their complex relationships. These agents interact based on rules. But the real value is that these interactions can lead to outcomes you never predicted.
So it's about capturing what they call emergent phenomena.
Exactly. Think about simulating a disease outbreak, or testing new traffic patterns in a city, or, in a defense context, helping militaries prepare for those really rare events. The situations where you just have no historical, real-world data to look at.
And finally, we get to the big one. The tech that generates our deepfakes and dominates all the headlines, deep learning algorithms.
Right. Deep learning uses what's called representation learning. It automatically analyzes and learns the features and statistical distributions from huge training data sets. And then it generates completely new data that follows those learned patterns. The applications, especially for visual data, are theoretically limitless, and it requires very little human supervision.
Within deep learning, you always hear this debate, this trade-off between the two big models, GANs and diffusion models. Now, we know GAN's generative adversarial networks, they're the old workhorses. They're known for incredible realism, but they can be unstable to train. What's the major security risk they pose?
The security risk is that GANs work by trying to directly mimic the training data. And that means they might inadvertently or accidentally reproduce sensitive private information straight from that original training set.
And then you have diffusion models, the newer player on the block.
Right. They're more stable, they're easier to train because they don't have that adversarial competition that GANs do. And they're gaining huge traction because the process itself, which involves adding noise and then learning to remove it, inherently makes it harder to reproduce the exact training data. So that offers a distinct privacy advantage.
Okay, now here is the really counterintuitive thing I found in the sources that I think you need to explain. If they offer this great privacy advantage by not copying directly, how can the research also say that diffusion models are the least private form of image generation compared to other techniques? That seems like a total paradox.
It is a fascinating trade-off, isn't it? While the diffusion models prevent that direct copying, the underlying math means that information about the statistical distribution of the training data can still be extracted or inferred more easily than from, say, a VAE.
So you protect the specific image,
But you might inadvertently expose the overall characteristics of the whole dataset used to train the model. You're shifting the privacy risk from one specific example to the generalized knowledge the system has learned.
And speaking of that, you mentioned diffusion models are computationally intensive. Why is that process of adding and removing noise so much more resource heavy than what GANs do?
It's because it's an iterative, multi-step process. Diffusion models build an image by starting with random noise and then repeatedly applying a learned function to gradually remove that noise and refine the image over hundreds, sometimes thousands, of steps. All those little steps to get to the final image require immense compute power, much more than the sort of single pass-through methods in older architectures.
Okay, so let's take all of that, the stability of diffusion, the realism of GANs, the risks, and apply it to the big picture, international security. This is where proper training is absolutely vital, especially for autonomous systems making decisions in theater.
Yes, and that brings us to this concept of edge analytics.
For our listener, why is it so critical for these autonomous systems to operate at the edge?
Edge analytics just means the data is collected, processed, and acted on immediately, right on the device itself, at the edge of the network, far away from a central cloud server. And this is critical because in combat, you cannot afford latency. A drone detecting a threat can't wait even milliseconds for a signal to bounce back from a server thousands of miles away.
And synthetic data ensures these systems are trained for those complex scenarios with zero latency.
Perfectly trained for them.
The value-added benefits here are just immense, beyond just speed. The sources point to 4 key areas. First, training and efficiency.
Right.
You can shorten training cycles dramatically, and you can practice for those, black swan events you can't ethically or practically recreate in the real world. Second, it overcomes constraints.
Which is a huge one.
If you have a spy drone that only flies at high altitudes, its data is useless for a ground robot. Synthetic data can just generate that low-altitude environment it needs.
Third, and this is a massive advantage for international cooperation, is the legal benefit. By using simulated artificial data for training, militaries can sidestep a lot of the legal and regulatory headaches of collecting, storing, and sharing highly sensitive, real-world data with allies. It just greases the wheels of collaboration.
And finally, the operational advantage. This lets you handle those 3D missions.
The dull, dirty, and dangerous.
Exactly. You can put systems into these highly dynamic, multivariate environments where a human operator's life would be at risk. It reduces human exposure immediately.
But we have to acknowledge the risks that come with this. Synthetic data still struggles to fully replicate the complex physics of the real world, the subtle ways gravity and friction and light all interact.
And that bias problem we talked about earlier.
It comes right back. If the real-world dataset you use to train your generator is already skewed with gender norms or racial norms, the synthetic data won't just reflect those flaws, it will often amplify them.
So if you use biased synthetic data to train an autonomous weapon system, what's a real-world consequence?
The consequence is mission failure. Or worse, incorrect identification or targeting. An autonomous system has to operate on ground truth, not amplified cultural assumptions. This is why verification is so critical. And of course, there's always the threat of data poisoning, where an adversary intentionally injects bad data into the pipeline to degrade the system.
Which is fascinating, because what we're finding is that AI is also the only viable defense against AI.
In the cyber realm, absolutely. AI acts as a force multiplier. The digital landscape is just exploding in scale and sophistication. We need AI to provide enough eyeballs to supervise all the pressure points in a network. Defensive AI is the only way we can hope to fight back against AI-enhanced offensive attacks that use these synthetic images or deceptive techniques.
That completely shifts the problem. If AI is generating the attack and AI is providing the defense, then the ability to detect if the content is synthetic becomes the decisive battlefield, and that's where the Aloke benchmark comes in.
Aloke AI is a critical new tool. It's a benchmark that evaluates large multimodal models, or LMMs, on their ability to detect synthetic data across 5 different types: video, image, 3D, text, and audio.
And the multimodal part is key.
It's everything. It means these models are designed to process and relate information from all those different formats at once, which makes them our best shot at a general-purpose detector.
And looking at what LMMs struggle with now, that basically gives us a roadmap of where the synthetic tech is winning.
Exactly. Deepfake detection is still immensely challenging. It requires this really nuanced perception of fine-grained forgery features. For instance, even a powerhouse model like GPT-4o performs pretty poorly when you test it specifically on deepfake content, compared to its overall accuracy.
Why is that?
It's connected to specialized knowledge gaps. LMMs are great with common images, objects, landscapes, things they've seen millions of times, but their performance just deteriorates when they face expert domains like satellite imaging, medical scans, or complex legal documents. They fail because detecting forgery there requires domain-specific knowledge they just don't have.
They need to know the physics of spectral bands in a satellite image or the biology in an MRI.
Knowledge they lack because their training is so generalized from the open internet.
But the most telling signs of artificiality, the real glitches in the matrix, are those synthesized artifacts that just violate basic physics and temporal consistency. Give us some of the classic examples they're spotting.
Oh, they're delightfully bizarre. You see things like sand transforming into plastic and then into a chair that just floats in midair.
Wow.
Or a video of a basketball passing directly through a hoop without touching the net. In animations, you see jellyfish tentacles that unnaturally merge into one and then split apart again. These physics violations are the digital fingerprints left behind by the generation process. The system just hasn't fully mastered the rules of our reality.
So spotting the forgery is one thing. But how do you ensure the expensive synthetic data you've made for a high-stakes job is actually good for training? You can't waste years training a model only to find out the data was flawed from the start.
And that's where the breakthrough of the synthetic data quality metric, or SDQM, comes in.
SDQM.
It solves that exact problem. It's designed specifically for object detection datasets, the kind used to train vision models like YOLOV11. It integrates multiple submetric into one composite score that predicts how effective a synthetic dataset will be.
What are the key parts of that score?
The most critical part is something called the mathematical information. It mathematically measures the statistical usefulness of the synthetic data compared to a real-world reference. It also includes things like better recall and pixel intensity match.
Why is having a single metric like this such a monumental breakthrough? How do we quantify its predictive power?
It's all about the correlation. The crucial discovery is that SDQM strongly correlates. We're talking a correlation coefficient of pivotal 0.87 with the final model performance score, which we call the MAP50.
Okay, for the listener, what is the MAP50 score?
The MAP50 mean average precision at 50% intersection over union is essentially the final grade. It's the accuracy score for an object detection model.
Yeah.
It tells you how well your model actually detected and identified objects in the real world.
So a correlation of 0.87 is huge.
It's massive. It means this metric can predict with extreme accuracy the success or failure of a model before you run the expensive training cycle. And that predictive capability saves immense computational resources, time, and money. It makes defense development dramatically more efficient.
So we've arrived at this really fascinating, complex reality. Synthetic data isn't some fringe idea anymore. It's maturing. It's essential for training the next generation of AI systems that are vital for international security.
And yet, its proliferation brings these major risks: misinformation, deepfakes, the amplification of insidious biases.
Right. The next generation of data isn't just mimicking reality. It is the foundation that future autonomous systems are being built on. The information that systems are trained on may soon be predominantly constructed, not observed.
Which leaves us with a final provocative thought. Given that AI is the necessary defense against this accelerating wave of AI-enhanced attacks,
And given the massive saturation of synthetic content online,
will we reach a point where our most critical autonomous defense systems are trained primarily on simulated data just to navigate a digital and physical environment that is, by definition, mostly constructed? This reliance on synthetic data may inevitably create a new, distinct, synthetic reality that only AI can reliably operate within, putting an entirely new burden on human analysts to somehow bridge that gap.